I'm not sure how it's, no, maybe that lecture was a bit short. But anyway, we've got to calculate this integral. So this is 1 over 2L minus L to L of e to the I k n x c naught of x dx. So what we do is we're going to do this by the simplest possible way, not by some clever integration rule. We're just going to use the midpoint rule. So we're going to divide it to xm is equal to minus L plus L 2Lm over n. So we're basically dividing this interval into a sequence of points x0, x1, dot, 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 and the final one is xn. Alright, so this integral here is going to be approximately the sum of e to the I kn x m times c naught of xm. So c naught of xm is a value of this function in a discrete set of points. So this is a vector, a sequence of points. And then we've got to multiply it by the delta x, which is 2Lm over n. So we've got to multiply by the delta x. So that's how much. So that's each time. What's the spacing here? That's delta x here, which is equal to 2L over n. So that's 2L over n, and then of course we divide by 2L out the front. So I'm going to run out of space here, but they're going to cancel. Maybe that's the easiest thing to do. I'm going to lose that 2L, and there's my sum. So this is sort of starting to look a bit like the fast Fourier transform, the discrete Fourier transform. And this is from n equals 0 to n minus 1. So I'm m. Now, we've got to go back and go, don't delete this. What do we know? We also know the following. We know that Kn is equal to pi n over L. So if I come down here, I get the sum 1 over n from m equals 0 to n minus 1 of e to the power of I pi n, and then xm, right, pi n over L times xm, which is minus L plus 2Lm over n, c naught of xm. And then I can simplify this. So I get e to the I pi times n So now we're going to talk.
We can solve this equation by observing that the a plus b
is an algorithm, right? Because they implements the
is equal to minus kab plus
I've already
kab.
met this before.
So this is 0.
So we're just going to understand a little bit more in detail about how it works.
So we can go
This is almost
a
exactly
plus
the
b
formula, not for the
whatever we
Let's look
started
at this.
with.
Let's imagine
We know once we can substitute that,
We're
and
doing
then we
these
end up
variables.
with
We just came about finite
the
way we
ADT
started.
is
You
equal
would
to
have
minus
minus
k.
cancels anyway, and it doesn't matter.
Might as well follow
Essentially, we're going to do it numerically.
the
Even if we're going to go from minus to discretely, we're going to have to go from minus to L. We can't get Fourier series solution discretely by doing this very naive discretization. So we obviously would make, if you want to go into the details of weight and try and be minus, but normally do this integration by Simpson's rule or something clever, Gauss-Legendre quadrature. But if we do it just by the midpoint rule, we do a Fourier series formula for the vast solution on the Fourier transform. Okay,
So
the discrete Fourier
K,
transform at least, and the
K,
coefficient, which is the fast Fourier transform, but it's the same
plus
algorithm.
b minus b.
I'm just using K in here, but unity of. Okay,
All right.
the next thing to do. UIDT of C in hat.
e to the I k in x.
The next thing is to go back to the actual solution here, which is that
the sum from n equals
we know that
minus
C of
infinity
x m comma t
to infinity
is equal
of
to the sum
minus k n
of
squared
infinity of
c n
c naught
of
t
t
hat.
e to the I k in x. And then of course that means that
Okay,
each of these, the t c n hat,
c n hat naught. Just
is equal
calculate
to
it.
minus k n
Multiplied
squared
by
c n hat.
e to the minus k n
You know
squared
from the
t
orthogonality of
d
for a series, so we get
e to
c n
the
hat
I k n
is equal to
x m.
c n hat at naught.
And then if we substitute
This is a
that,
function of time. E to the
our expression
minus
for x m
k
and
to the,
k
I've got my
n,
d
what we
here, haven't I?
get
Given to minus k n squared dt. Okay, so therefore we've got this expression for
we get
the
c n hat,
solution.
and we end up with an e to the minus I pi n. Okay, to cancel this plus 1 times
E to the minus k n squared
e to the
td
minus k
under
n
e to the I
squared
k
dt
x. So that's the solution to the
power
equation.
of 2i.
So now we've got to try and solve this
n.
numerically, right? We're going to try and do this integration. And we
Alright.
also know that
So,
we can calculate
this-
what C in
Okay, we've got to
naught is.
multiply by this term here.
as well
This
from the
term
Fourier
here, c
series.
naught times e to the
Write that
minus
down
I pi
here.
n is by definition, we can cancel that out, and it's the sum here from m equals naught to
So
n minus
c
1.
n
So essentially what this is telling
at
us is,
naught
we've just, by
is-
doing this implementation, we've shown that the exact,
The
because this is
integral
exactly the
of-
expression for the discrete
which
Fourier
from
transform. So
minus
we take the
infinity
discrete
to
Fourier transform, of course,
minus
you know
L to
this extra
L.
term here, but it cancels
e
out
to
here
the
when we go
minus
back.
I
So we can just
k
ignore it.
n
And we then take the
times c naught of x.
Fourier transform, and the what divided
So
by
these
n
are
doesn't matter
formula
where it
here. So this is the
appears. You can
solution
do
to this
one
equation,
Fourier
right?
one versus long
Written
as
down.
one
It's
is
just separation of variables with a
expression
head
is
is fine,
fine.
basically.
We
And
can carry
nothing
it
more than
through.
that.
Okay, so we're basically showing
So
here
this is the
that
expression
just
here.
this implementation by solving the
Assuming
diffusion
that the
equation by
solution,
doing this
all I've done is
discrete
assume the solution is
sequence of
periodic,
points,
which is the bounding
leads us
conditions
to the
of the
formula
finite
to try and
model.
solution via the
Make this
discrete
infinite.
Fourier
Okay?
transform.
You don't want to have any effect from the wall. So what we've got